Hello, I'm Kshitij Saxena, and I'm delighted to present the first lecture in series on traction power systems. The topic of my presentation is Understanding DC traction power systems from a systems engineering perspective. Let us first go over what is covered within this slide. We will first discuss about importance of systems engineering, and definitions of system, subsystem, element, and interface. We will then move on to what is a traction power system and what are the subsystems within traction power system. We will then describe functional elements of a traction power system and what is meant by functional analysis. And then I will describe the interfaces of traction power system and how to do interface management. And finally, I will conclude with the next steps. Systems engineering is a transdisciplinary and integrative approach to enable the successful realization, use, and retirement of engineered systems using systems principles and concepts and scientific, technological, and management methods. Systems engineering provides facilitation guidance and leadership to integrate the relevant disciplines and specialty groups into a cohesive effort, forming an appropriately structured development process that proceeds from concept to production, operation, evolution, and eventual disposal. Systems engineering considers both the business and the technical needs of the customers with the goal of providing a quality solution that meets the needs of users and other stakeholders, is fit for the intended purpose in real-world operation, and avoids or minimizes adverse unintended consequences. The goal of all system engineering activities is to manage risk, including the risk of not delivering what the customer wants, the risk of late delivery, the risk of excessive cost, and the risk of negative unintended consequences. One measure of the utility of systems engineering activities is the degree to which such risk is reduced. Conversely, a measure of acceptability of absence of a systems engineering activity is the level of excess risk incurred as a result. What is a system? A system is an arrangement of parts or elements that together exhibit behavior or meaning that the individual constituents do not. Hence, a traction power system, shown with the purple box, can be defined as an arrangement of individual elements that aim to provide DC propulsion power to the trains for operation. The individual elements that make up the system cannot on their own accomplish this task. A subsystem can be defined as an organization of system elements into a group based on relative strength of element cohesion. So a traction power system can be divided into a traction power substation subsystem, shown within the red box, which comprises of all the elements of the traction power system within the traction power substation room, and a trackside power equipment subsystem, which is shown within the orange box. In case of the third rail electrification, comprises of trackside power distribution equipment such as the power disconnect switch and the grounding switches. A set of elements constitute a system. A system element is a discrete part of a system that can be implemented to fulfill specific requirements. A system element can be hardware or software, data, human processes, procedures, facilities, materials, or any combination. A TP traction power system elements are shown within the red dotted boxes. An interface is a point of connection of two or more components for the purpose of passing information from one to another, shown here across a blue line. The goal of a traction power system is to provide propulsion power to the trains, enabling them to move on the tracks. Such a system collects power at the medium voltage from the utility and transforms it using specialized equipment to power rails and catenary wires. There are two methods of power collection. First, via power collector shoe at the bottom of the train, and the second, the train's overhead pantograph that collects power from the catenary wire. Whether a third rail or an overhead catenary system will be used is decided by two factors: the propulsion voltage and the layout of the train system. For example, transit systems with dedicated guideways within elevated or underground structures where people and traffic cannot be in proximity with power are mostly third rail systems. On the other hand, transit systems that share the roadway and may have possibility of proximity to passengers, traffic intersections, and road traffic are mostly overhead catenary systems. The diagram here represents the elements of a traction power system starting from the utility and medium voltage AC switchgear up top, transformer and rectifier in the middle, and DC switchgear to distribute the power to the trains via a third rail or an overhead catenary system. What is a functional element? Each element of a traction power system has a specific function. For example, medium voltage AC switchgear distributes the medium voltage AC power from the utility across the transformer for further processing. SCADA, or Supervisory Control and Data Acquisition System, comprises of several programmable logical controllers in constant communication with one another, aided by high-speed optical fiber communication on one hand, and with the switchgear and traction power substation on the other hand, to monitor and control all the traction power equipment. Every element here performs a certain function, and a logical arrangement of these elements fulfills the goal of a traction power system. What is functional analysis? A part of system decomposition and definition process, the purpose of functional analysis is to divide the complex system into smaller, simpler parts so that eventually they can be individually designed. For example, the function of a transformer is to accept medium voltage and step it down to low voltage. The transformer is a system element within the traction power system. However, a transformer designer could further break down the transformer into its constituents, which have their own specific functions to perform, such as the core of the transformer, winding, insulation, power terminals, controls, etc. Functional flow block diagram is a popular graphical method for functional analysis. It shows the input on the left, like AC medium voltage, output on the right, like AC low voltage, control at the top through SCADA, and mechanism at the bottom, which is a process to step down the voltage. Such a breakdown into individual elements is very useful in requirements management. Each requirement must be validated or verified through testing. Most importantly, functional analysis, like all other parts of the design process, is not just done once and then finished. It evolves and could be revised as the design progresses. What is an interface? This diagram shows various traction power interfaces where power, energy, or data is passed from one component to another. Consider, for example, the traction power and blue light station safety relay panel interface. This is essential for safety. An emergency push button is provided at the blue light station, which enables cutting off power supply in the area. Some blue light stations also have a push-to-talk push button, which enables voice contact with the emergency handler. This brings into picture an interface with communications. A safety relay panel integrates contacts from various push buttons and uses them to intelligently remove power supply to a portion of the track. The blue light station, the safety relay panel interface, spans several system engineering disciplines, such as with communications for the push-to-talk functionality, with the power rail, which enables de-energization through opening of feeder DC breakers, with the central control, which provides the alarms, log, and action by the operator, and with train controls bringing the train to a standstill, besides the DC switchgear. A traction power interface is managed using an interface control document or an ICD, or design drawings co-developed by the respective discipline leads through extensive deliberations, followed by multidisciplinary review and a formal sign-off. Requirements that were examined through functional analysis must be verified using certain tests. An ICD provides clear information between various disciplines that collaborate to make the system work such that there is common understanding of the requirement and its function. Let us discuss using an example of the blue light station and safety relay panel. Firstly, an interface drawing providing the detail of the location of the blue light stations, wiring of the blue light stations, and their trip zones is developed. This provides a SCADA engineer to program the programmable logical controller so that the power rail de-energization happens through opening of the feeder breakers or the disconnect switch. This drawing also provides information to the electrical installer about how to wire blue light stations contacts with the safety relay panel, connection to the safety relay panel to the PLC, and finally into the opening circuit of the feeder breaker. How to verify whether a blue light station does its intended function? One must test the functionality across several interfaces and elements as described earlier. So a test procedure is written such that we verify whether pushing a blue light station de-energizes the power rail segment it is intended to. For example, a drawing that shows a blue light station located at the east end of the station platform at the northbound track. When pressed, de-energizes the entire length of the northbound track power rail corresponding to that side of the platform. This will cut off the power to the train, and thereby this is a safety or an emergency function. To conclude, this presentation provides a system engineering analysis of DC traction power system. This is necessary because there's a dearth of information regarding systems architecture of DC traction power systems, and there are differences in voltage levels and power collection technologies. Systems engineering helps to understand the elements of a DC traction power system through decomposition and their functional requirements. An attempt to apply functional analysis and describe various interfaces of DC traction power system was made here. Effective interface management enables clear design and verification objectives through testing. I hope that the material presented here will enable the audience to gain an understanding towards meeting the various standards, including CENELEC. I hope you enjoyed this presentation. I look forward to your suggestions and questions. Thank you.